In this algebra video, we're in Chapter 10, Lesson 2. We're going to talk about simplifying radical expressions. As a heads up, we're going to primarily focus on square roots, meaning roots when there's an assumed 2 here. I'm not going to spend too much time in this video talking about cubic roots, that's a 3 out there, or fourth roots. They all exist, but we're going to focus on square roots. And square roots tend to have no number out there, so you assume it's a 2. So that's what we're going to talk about. Anyway, our objective is, as the student, I can simplify radical expressions by using the product and quotient properties of square roots because I will factor fully and look for repeats because these repeats would indicate I have perfect squares. Now I'll show you why you want to do that in the process. Let's get some basic vocabulary out of the way. When I say radical, I'm referring to that checkmark looking thing. It's like a combination of a checkmark and a division sign. That's a square, a lot of people call it the square root symbol. But it's technically only called a square root when there's a 2 here or when there's nothing there. It's assumed to be a 2. It's really called a radical or a root if the number outside tells you which one it is. So that would be a cubic root or a third root. Anyways, that symbol is called the radical. The stuff inside of it, so if I have, let's say, 49 in there, 49 would be my radicand, meaning what is the square root of 49? And you know that would be 7. That's kind of what I'm talking about. So a quick reminder, a square root is the opposite of squaring something. So the square root of 49 is 7 because 7 squared is 7 times 7, that equals 49. Okay, so the square root of 49 is 7. That's what we're talking about here. Now, technically it's positive and negative 7, but we're not going to worry about the negatives and all that. We're going to be focused on just the simple positive versions. So the radicand's went inside. There's your basic vocab. Alright, so let's talk about your first property. This is the biggest one. This is the one that you're going to use the most to simplify most questions. Or most expressions or questions, when you start to simplify them, you'll start to use this property before it's over with. This is one we'll use the most. So we're going to spend the most time explaining this one. The product property. Basically, the product property says you have some stuff times each other underneath the square root symbol. You can give each of them their own square root. Now, that includes regular old numbers. So, regular old numbers such as, I don't know, square root of 15. You could think of the square root of 15 as the square root of 5 times the square root of 3, because 5 times 3 is 15. That's what I'm talking about. Except we're not just going to separate them any way you can separate them. There's usually a strategic way to do that, and I'll talk about how to find that. The whole point of this, though, is when we separate it, the whole point of separating is what I have here in blue. We're looking to see if one of those things has a pretty square root, meaning one of those things is a perfect square. Now, look at this one that I've already done for you. The rest of them we'll do together. Let's say square root of 45. Well, square root of 45 is also 9 times 5. That equals 45. We strategically do that because we know the square root of 9. We know that one. The square root of 9 is 3. And once you take the square root, once you take it, you have the 3, you no longer need, you do not put a square root symbol around it. You have 3. We do not have a pretty square root for 5. It's like 2 point something. It's an ugly decimal that goes on forever. But the point is, we do know this one. And so it's on the outside. And they're touching, that's multiplying. They're touching, that's multiplying. So you would read this as 3 times the square root of 5. Some of you might be thinking right about now, why? Why bother? Why simplify radicals? And the rationale behind simplifying radicals is very, very similar to fractions. Quick side tangent to give you kind of a reasoning why. Let's think of 7/9, for example. If you were to do calculations with 7/9, some of you are like, fractions, you want to turn it into a decimal. Well, if you go to turn this one into a decimal, it's 0.77777. It goes on forever. So you at some point have to cut it off and round. So if you said 0.78. Now, that's close to the value of what you started with, but that's not exactly right, and it's a little off. And you're going to be off due to what's called rounding error. So you're not being as precise, and that's why sometimes math teachers want you, not just math teachers, but in general, you want to keep them as fractions, because when they're fractions, like add, subtract, multiply, divide, you don't ever have to actually round, so you're more precise. So that's what we're doing here. We're going to talk about simplifying radicals because, for example, let's go back to my 45 example. Sorry about that. Because we're in our next video, we're going to talk about how to do operations with this, how to add, subtract, multiply, and divide. But you can't do that unless it's been simplified. kind of like finding common denominators. It's kind of going to feel like that. We're going to need like terms. You'll see what I mean in that video. But so I just want to take a moment to explain to you why do we want to simplify. It's going to help you be more precise. You're going to have less rounding error, but then you're going to be able to find like terms, or it's kind of, the metaphor. It's kind of like common denominators. You'll see in the next video. Anyway, some of you might be thinking, well, how do we know what to strategically factor this into? For example, why didn't we choose 15 and 3 right here? Why not 15 and 3? And that's what we're going to talk about. And the truth is, you could do either or, and I'm going to show you what I mean. So let's pursue this question. How do we know what to factor the radicand into? And the truth is, it doesn't matter what order you factor it. Just factor fully. And once you're done factoring, look for repeats. So let's do this example. Square root of 75, and I tell you to simplify. Well, some of you might be thinking, well, I know 25 and 3 equals 75. Or some of you are like, oh, hey, 25 is a perfect square. I know the square root of 25. It's 5. But some of you might be saying, well, maybe what if I didn't choose 25? What if I chose 15 and 5? That's okay. I'm going to tell you keep going. So go ahead and keep factoring. By the way, remember this is called a factor tree. Hope it looks familiar. If not, it's just basically a visual way of factoring numbers to find out what numbers times each other to give you the original number. Anyway, 15 we can find by 5 times 3. And so a factor tree works because if you take a calculator, you type in 5 times 3 times 5, or do it by hand, you'll get 75. So the fully simplified, not simplified, but the full factors, the prime factorization, that's the proper wording, but the prime factorization, meaning these are prime numbers. We can't go any further without using the number 1. Once you look at your prime factorization, you look for repeats. For example, you have a repeat of 5s. Because you have a repeat of 5s, that means one of the factors of 75 must have been 5 times 5, which is 25. And in fact, that was the first way you saw me doing it. But here's how it works. Think of it this way. I just switched the order, put them next to each other real fast so I wouldn't get as messy, but it honestly doesn't matter. Anyway, here's how it works. When you're going through this, you look for things that have repeats. So if you have a repeat, a story to remember this is think of it as having a friend to go outside and play with. So, for example, they have friends. So the number 5 has a friends. So when you go to rewrite this question, 5 gets to go on the outside of the square root. 5's on the outside. 3 does not have a friend with. Therefore, 3 has no friends. So 3 doesn't get to go outside and play. So 3 is stuck on the inside. So the square root of 75 simplifies to 5 times the square root of 3. Some of you might be thinking, well, how do I know if I'm correct? I don't know if I've done this correctly. How do I check myself? The beauty is you can. It's just like checking fractions. Back when you weren't sure if you simplified a fraction correctly, you could actually check it by using a calculator and dividing. 7/9, like for example, if you thought 14/18 simplified to 7/9, but you weren't sure, you could divide, and you would get 0.777 for both of them. They have the same value. So that's a way to check. The same thing goes for radicals. Check with your calculator. If you type in 75 square root, you get approximately 8.66025. It keeps going on forever. It's an irrational number. That's one of the examples of irrational numbers. The square root of non-perfect squares. Because, for example, 8 times 8 is 64, 9 times 9 is 81. So this is between those. Anyway, to check this one, you type in 3 square root, or based on your calculator, square root of 3. And with that decimal on the screen, you press times 5. Well, the square root of 3 is 1.732, etc., etc. With that on the screen, press times 5, and you get 8.66025. I'm saying it slowly because I'm actually reading off the screen. And notice, it's the exact same thing. It's the exact same decimal, which that's your way of knowing that these two are equivalent, meaning they have the same value. You have simplified it correctly. That's how you can check yourself. So, factor them with a factor tree to your prime factorization. Look for doubles. Any doubles, meaning groups of 2, get to go on the outside. Well, some of you might be thinking, what happens if you have more than groups of 2? Let's take a look at this example. Some might be thinking, what if there's letters inside? So let's take a look at this one. Let's factor this one to simplify it. Let's start with the letters. The letters are the easiest things to factor, meaning what times what gives you 125x squared, y to the third power. The truth is, you know you'll have 2 x's in there, and you'll have 3 y's in there. You already can expect that. So now, when we go to do our groups of 2, that will not be hard, because you'll see, okay, I have one group of 2 of x's, I have another group of 2 of y's. Oh, this y, he has no friend. So that y is going to stay on the inside. So granted, I jumped straight to the letters, because the letters tend to be the easiest ones to do. So that other y had no friend, so that other y is going to stay on the inside. Okay, so now let's factor the 125. What times what gives you 125? And you might be able to come up with different things than me, but it doesn't matter as long as you go all the way. 25 goes in both of 25 goes into it, and in fact it goes into it 5 times. Well, we're done with the 5, but we keep going with the 25. The 25 turns into 5 times 5. So we can't go any further. That's our prime factorization, but now we can look for doubles. And you'll notice, it doesn't matter. They don't have to be next to each other. They can be ones that are away from each other. It doesn't matter. 5, 5, and 5, that's a double. So that means we can show 1 5 on the outside. Notice, this 5 does not have a friend, so this 5 stays on the inside. So once you have everything on the outside, you just multiply them together. Now, so the answer to this question, let's go ahead and finish this question, is going to be 5xy, 5 times x times y, times the square root of 5y. That's going to be the fully simplified version of this radical. Let's do a quick what if. Let's say you had also had a 6 and a 6 and, I don't know, a 7. So the double of 6's would have made it on the outside. She would have gotten to add a 6 out here. And remember, it's multiplication. And then 5 times 6 is 30. So if you have more than one number out there, it's okay. You just multiply them together. The same thing happens if you have something left on the inside. If you have a 7, like I said, and you have a 7 on the inside with it, you do 5 times 7. Well, 5 times 7 is 35. So you'd have 35y on the inside. So keep that in mind. If you have more than one number going on the outside or more than one number going on the inside, it's okay. You'll just multiply them together. Let me erase that what if. So now let's talk about our next property. Our next property is the quotient property. Just like the product property, it basically says you take what operation you have in there, in this case it's a division, and you can give each thing, the numerator and the denominator, its own square root symbol. So the square root of a divided by b, start by giving each of them their own square root. After that, you're going to do to the top and do to the bottom just like we just got done talking about. So as an example, if I give you the square root of 40 over 36, start by giving 40 its own square root, 36 its own square root. Now, simplify top and bottom as far as you can go. But when you simplify them, you're going to use what we just talked about, the quotient property. So let's start with the square root of 40. Maybe you'll hit pause and try this one on your own. Hit pause. Feel free to try this one on your own first. Well, square root of 40, that's 10 times 4. Well, 4 is known as 2 times 2. 10 is 5 times 2. Sorry, my 5s are getting kind of sloppy in this video. There we go, 5 times 2. Now you look for doubles. All right, we have a double of 2's, and they have no friends. 5 and 2 have no friends. So we're going to have 1 2 on the outside, just 1. So we're going to have 1 2 on the outside, and we're going to have a 5 times 2 on the inside. Well, 5 times 2 is 10, so we have 2 times the square roots of 10. That's what square root of 40 simplifies to. So put that as your numerator. Okay, so we simplify the top. Now let's simplify the bottom, square root of 36. Feel free to do this one on your own first. Hit pause, make sure you still got it. Square root of 36, we might be thinking of different things, but it doesn't matter. They all lead to the same thing. You might be thinking, oh, 36, that's an even number, so I know I can at least divide by 2. Well, I'm going to go with 9. 9 and 4 go into it. And 9 is 3 and 3. And 4 is 2 and 2. So let's see. We have a double of 3's. We have a double of 2's. Oh, hey, look at that. That means nothing is left on the inside. And some of you may have been thinking, oh, well, duh, I know the square root of 36. The square root of 36 is 6. And you're right. I just wanted to do an example where I showed you what happens if you have nothing left on the inside. So what it would look like this if you didn't notice. You would have a 3 on the outside, you'd have a 2 on the outside, and you have nothing left on the inside. And if you need something, put a 1 there. But the square root of 1 is 1, and when you multiply by 1, it doesn't do anything. So you'll never see me including that square root of 1. And just technically, if you want to know, it's there. All right, anyways, 3 times 2, well, that's 6. So even if you didn't notice that what you were simplifying was a perfect square, you would still do the looking for doubles thing, and then simplify, and you would still get the same number as if you had known. So 6, that's what our denominator is going to become. So we're home free. We've simplified the top, we've simplified the bottom, and you want to say you're done, you want to celebrate, but you got to remember all those old fraction skills. If you can simplify these regular old numbers, I want you to do it. So the 2 and the 6 do simplify, so the 2 divided by 2 is 1, 6 divided by 2 is 3. So you will have this. And like I just said, when you multiply by 1, it doesn't do anything. So you're going to notice most of the time I'm not going to write that 1 right there, but technically it's there if you need it. This would be our final answer. You don't need that 1. That truly is the final answer. And if you're not sure if you're correct, type in 40 divided by 36. Hit the square root button. Type in square root of 10. With that on the screen, press divided by 3. Then you'll notice you'll get the exact same decimal. That's how you know that you did it correctly. Alright, so this was the quotient property. Do the top, simplify the top separately, simplify the bottom separately, and then at the very end check to see if you can simplify any of the regular numbers. Notice, I did not divide that by 2. I did not do 10 divided by 2 and put a 5 there. That would be incorrect. And a way to explain that is technically it's a grouping symbol inside of a grouping symbol, and you can't go through 2 of them like that. So that's kind of one way to explain why you can't do it. So don't invade the inside of that square root with something that's not inside of a square root. Alright, so the 4 things I'm going to show you in this video: product property, quotient property. I'm not going to talk to you about something called rationalizing the denominator. Sounds so much more fancier than it is. I promise you it's pretty straightforward. We're going to practice it, and we're going to explain why and how it works. Alright, so what you need to know is this. You cannot leave a radical in your denominator. It's improper. It's imprecise. I've got reason to explain why, but just don't do it. So if you have a fraction, you start by giving top and bottom their own square roots, like usual, but you can't leave this here. You can't do it. And you might be thinking, well, let's try to simplify square root of 35. And you could try, but you get 7 and 5, 7 times 5. Those are both prime numbers, no doubles. So it actually doesn't simplify. It already is. Same thing goes for the 15. It's already simplified, so we can't try any of that. But you have to do something called rationalizing the denominator. What I mean by that is you literally have to turn the denominator into a rational number. Because right now, it's the square root of a non-perfect square, which I told you is pretty much the definition, but not really the definition. It's just the most popular version of an irrational number, the square root of a non-perfect square. It'll be an ugly decimal. We don't want it down there for different reasons. Yeah, it's improper. It's a rule because I said so. But a way to remember it is also, technically, if you wanted to know what this equaled, you would do 35 square root. You'd eventually have to round. You would do square root of 15 square root. You'd eventually have to round. Then you would divide those two, and then you'd still have to round. So you'd be rounding 3 times. So what I'm going to show you is we want to see like a regular number down here, like 3. I'm just making that up. A regular number so that we don't have to divide by a rounded decimal. That way it's 1 less time we would round. That way we don't have to round. That way we would only have to round 2 times rather than 3. And it'll help make it be more precise. But the truth is, I'm never really going to ask you to turn these into decimals, but it's a good way to check yourself. Alright, anyway, so how to rationalize your denominator. You're going to multiply top and bottom by the same thing. And that thing that you're multiplying by is going to be the square root of 15. It's going to be whatever it is on the bottom. Whatever radical is on the bottom, that's what you're multiplying by. We're allowed to do this because something divided by itself is always 1. So technically, this whole fraction equals 1. We're multiplying by 1. When you multiply by 1, it doesn't do anything. We're going to make it look different, even though it's going to have the exact same value. So now let's talk about multiplying square roots. You kind of may have already figured it out. It's already related to the product property, what we've already been doing. But that's what we're going to talk about now. I'm going to do the bottom first, since it's the easier one, and then I'm going to do the top. They're both pretty easy, but the bottom is the easiest. Square root of 15 times square root of 15. The product property tells us if we can separate things, we can do the reverse and put them together. Well, 15 times 15 is 225. So we would have the square root of 225. Then you could use your calculator. What is the square root of 225? And the square root of 25 is exactly 15. No rounding. 225 is a perfect square. It has a pretty square root. Some of you might be thinking, well, hey, that looks familiar. We just had a 15. And you would be correct. The shortcut is the square root of something, I don't care what that something is, times the same square root of the same something will always equal that something. So the square root of 100 times square root of 100 is 100. It's that simple. The real reason is, technically it's 10,000, but the square root of 10,000 is 100. Notice, no square root symbol. It doesn't go there because it just equals. The value of it is 100. So let's go back and put a 15 on the bottom. Well, we've met our goal. The bottom's a rational number. Now, let's take care of the top. Square root of 35 times square root of 15. Square root of 35 times square root of 15. Well, that equals a square root of 525. But now, let's see if we can simplify that. If we simplify that, you're immediately going to split it right back into 35 and 15. So if I were you, I wouldn't even bother multiplying these together. Just put them side by side and start factoring and start working it from there if you can. Otherwise, you're going to do it, multiply to get 525, and then just start factoring to go right back to where you just came from. It's up to you. I'm going to do it just to show you where it came from. All right, so 35 is 7 and 5. 15 is 5 and 3. We've gone all the way we can. That's the prime factorization. Well, 5 has a friend to play with, so he gets to go on the outside. 5's on the outside. 7 and 3 do not have friends. 7 and 3 are stuck on the inside. And 7 times 3 is 21. So we have 5 times the square root of 21. That is the full simplified version of our numerator. So I'm going to go put that on top of the fraction. Okay, so we have rationalized our denominator. We have a simplified version, but you got to do what I already said in the last example. Check to see if your regular numbers also simplify. And in this case, they do. 5 over 15 does simplify. It simplifies to 1 over 3. So this is it, except like you already heard me say, I'm not going to include that 1, so I'm just going to say the square root of 21 divided by 3. That is the full, finally simplified version of this radical. Now, you could test it by checking the decimal. I've already said a few times you could do it, and you'll notice it'll be the exact same decimal as what we started with. So we're in business. So that's how you rationalize the denominator. Now, let's do a quick what if to make a point. Even if there had been a 3 down here with that square root of 15 already, you still would have only multiplied the top and bottom by square root of 15. But the only thing is once you had 15 down here, you would have a 3 right next to it. So you would have done 3 times 15. And well, 3 times 15 is 45. So you would have had 45 on the bottom. So just keep that in mind. Even if you already had a number down there, that's okay. You still only multiply it by what the radical is. Now let's do another example of that. Take a moment. Try this one. See if you can simplify this one further. And I'll give you a hint. You could simplify that square root of 12 first, and then you can rationalize your denominator. You don't have to, but you can. Give this one a shot. Alright, give them each their own square root. Excuse me, getting over a cold. Now, simplify the square root of 12. Prime factorization of square root of 12, we have double of 2's. 3 does not have a friend, so 3 stays on the inside. So we'll have 4 times the square root of 3. That's what that simplifies down to. Alright, so your top is square root of q, your bottom is 4 times square root of 3. Now, you have to rationalize the denominator. You cannot leave that square root of 3 down there, so you have to multiply top and bottom by square root of 3. That's what you're multiplying by. So now let's show our work for that. I'm going to go ahead and do the top first. I decided to do the top first because it's super easy. Square root of q times square root of 3 is just stick them together. 3q. That's it. That's all the top equals. Now let's take care of the bottom. Okay, so for reasons we already said, square root of 3 times square root of 3, that equals 3. Technically, it just equals 3. But technically, if you want to show your work for it fully, you could say, okay, 4 times the square root of 9, because square root of 3 times the square root of 3 is 3. Well, the square root of 9 is 3, so you're left with 4 times 3, and 4 times 3 is 12. So if you want to fully show your work, include this step in there. Or, I don't mind if you jump to this step, because it's always the case. It's not really fancy. It's just a way to say you know it equals 3. Alright, so the bottom of our fraction equals 12, our denominator. So I hit pause to check my answer, and I found I had a mistake because I'm rushing like I usually do. So the bottom of this does not equal 4 squared to 3. The bottom of this, we had a pair of 2's. I'm sorry if I drove you crazy thinking, what is this guy doing? You should have 1 2 on the outside and 1 3 on the inside, so it's 2 squared to 3. That's going to change a couple things. I'm going to show you. This is going to be a 2 squared to 3 down here, so it's going to factor answer over here. So that means the bottom of our fraction really equals 6. My apologies. I know eventually you're going to get tired of this guy. He keeps making these mistakes. You're eventually going to forgive me. You're eventually going to stop forgiving me. The good news is I usually catch my mistakes and I fix them. And I'll eventually learn how to use video editing software to go back and fix this. You never see it, but it's there. Now, I caught that mistake, and you could catch that mistake by checking the decimal, seeing if it's equivalent. When you have a letter like this, make up a number for the letter. For example, let's pretend Q was, 3. Do 3 divided by 12, hit the square root button. Okay, now if you would put a 3 over here like I said, then you get 9, take the square root, it's 3 divided by 12, because remember I originally said it was 12. It was a different decimal, so I knew it could not have been correct. So do a test experiment like that, and that's when I realized, oh, I made a mistake, and it was in one of my mistake was in one of my rush steps was doing that. My apologies. Hopefully you don't make the same mistake, but now you should know how to catch it. Okay, no more mistakes from here on out. I'm gonna do one more concept with you. I'm gonna show you how to do it with a more complex denominator, and then we're gonna be all done. We're gonna do a slightly more complicated example. I'll briefly show you why it works and how it works, and then we'll do it. We're gonna basically simplify this, and we're gonna have to rationalize the denominator. But here's the thing: you don't just multiply top and bottom by the square root of 5. That's not good enough. That worked before, because in our last example, we had nothing but multiplication on the bottom. So you're allowed to multiply and move stuff around. But in this example, we have addition or subtraction. It works the same way. So we can't just multiply by the square root of 5. That's not how we're going to have to do this. We're going to have to do something called finding the conjugate. It's super basic. It sounds harder than it is. The conjugate of the bottom is 4 minus square root of 5. Notice it's literally just negating the second term on the bottom. Negating meaning the opposite sign. So if this had been subtraction, you would have seen me do plus right here. But since it's addition, when you negate that, you do the opposite, and that's subtraction. So you multiply top and bottom by the conjugate. It's a fancy word that basically says it's kind of like a binomial, two terms, but you are doing the negation of the second term. You do this because, quick side experiment, back when we learned how to multiply binomials using the FOIL technique, and specifically it was in the video on special products. I don't remember if I made a video on that or if we just did it in class. But if you have the second term in each of these is the same but the opposite, you'll notice something happens. You'll notice that the middle two like terms, they will be exactly the opposites. They'll cancel because negative 5x plus 5x is 0. So this would simplify to x squared minus 25, meaning there was no middle term, no x to the first power. And that was one of those special products we talked about. I didn't call it that back then, but technically these were conjugates of each other. That's what we're going to do. We want the middle term to cancel out because in our case, the middle term is going to be square root of 5, and that's going to cause it to cancel out because we know, because this is the FOIL technique. This is a binomial times binomial basically. We know what the square root of 5 is. Square root of 5 is 5. Fantastic. But then we still have that middle term, and I'll show you what I mean. Let's show our work for it. But it will cancel out. Alright, so if we multiply these together using the same foiling, double distributive property, whatever you want to call it, same technique, 4 times 4 is 16. 4 times the negative square root of 5 is negative 4 square roots of 5. That's it. Just put them together. A positive times a negative is a negative. Now, square root of 5 times positive 4, well, that's just positive 4 times the square root of 5. You literally just stick them together. It's like saying, what is x times 4? It's 4x. Now, for the end, square root of 5 times negative square root of 5. Well, that's going to get positive times a negative. If you need to, pretend there's a 1 in front, if that would help you. It's going to be negative. And now square root of 5 times square root of 5, well, that's just 5, for the reasons we've already said earlier in this video. Now we combine like terms. We have like terms right here in the middle. We have minus 4 square roots of 5 and plus 4 square roots of 5. Well, those are exact opposites. They cancel. And we're left with 16 minus 5. Notice, the square roots of 5 are gone. And that's the whole point. We want them to be gone. So we have 16 minus 5. Well, 16 minus 5 is 11. So that means our denominator equals 11. So the denominator equals 11. We've rationalized it. It's a rational number. So now let's take care of the top. The top is a whole lot easier than the bottom. So now for the top, it's just the regular distributive property. Multiply these out. 2 times 4 is 8. 2 times negative square root of 5 is negative 2 times square root of 5. That's it. So now that's your numerator. So you've now rationalized your denominator, and the last thing you do is check to see if you can simplify anything. Look at your regular numbers. Is there something that goes into all of them? In this case, there is not. One, because 11 is prime. But it doesn't simplify any further. So this is your final answer. This is the fully simplified version of our original. So if you've gotten that as an answer or anything to a question, but the truth is, I'm mostly in Algebra 1, you're just going to be given that and be told to simplify it farthest to its very end, fully. There we go. So that would be its fully simplified answer. Now you're going to do one. Alright, here's your example. I want you to give this a shot. Remember to multiply top and bottom by the conjugate. The conjugate of 2 minus square root of 3 is 2 plus square root of 3. Now show your work. Distributive property up top gives us 6 plus 3 times the square root of 3. Now let's do the bottom. The bottom takes a little bit more room to show work. I'm doing another page so I can use the FOIL property or the double distributive. Alright, so go ahead and use the distributive property twice or the FOIL technique, whatever you call it, and let's simplify. 2 times 2 is 4. 2 times the square root of 3 is positive 2 times the square root of 3. Now let's do the other one. Negative square root of 3 times 2 is minus 2 times the square root of 3, because a negative times what's technically a positive is a negative, and that's why you see me put that minus sign right there. Now, negative square root of 3 times positive 1, again, pretend there's a 1 in front if you need to. That's what's negative, not the thing on the inside. So you're going to get minus, well, square root of 3 times square root of 3, that's just 3. Well, these like terms in the middle cancel because they're the exact opposites of each other. And you're left with 4 minus 3. Well, 4 minus 3 is 1. So the bottom equals 1. So the bottom equals 1. So you're dividing by 1. Does it do anything when you divide by 1? No. So the answer is just 6 plus 3 times the square root of 3. Now, as a side note, if the bottom had been something, let's say 9, you would look to see if, we are done by the way with this example. Now I'm just going to do a quick what if and the video is over. But if that bottom had been, say, a 9, you could simplify these 3 things if something goes into all of them. And in my example, 3 would go into all of them. So if I put a 9 right here, if there was a 9 down there, you would be able to simplify. 3 goes into 6 2 times. 3 goes into 3 1 time. So we'd have 2 plus 1 times the square root of 3. Well, 1 times the square root of 3 times by 1 doesn't do anything. So you would just write square root of 3. 3 goes into 9 3 times. So this would have been the fully simplified version if there had been a 9 down there instead. That was just a quick what-if question. Alright, so ladies and gentlemen, final answer. We have talked about simplifying radicals. This is the foundation of everything you need to do operations with radicals. So this is the bedrock to do operations, because to do operations, you're just going to simplify everything fully, then do what it says, using the skills we've already talked about. Alright, take your notes, ask questions. We'll go further with this in class. You guys take care.